This is the screencast for section 3.4, example 4. We're going to model vertical motion, which is definitely related to pre-calculus. We did a lot of vertical free fall in motion there, but now we're going to add the calculus element to it. We have a dynamite blast that propels a heavy rock straight up with a launch velocity of 160 feet per second. So that's the initial velocity, 109 miles an hour, fine. It reaches a height of s, so its position in this case is a height, equals 160t minus 16t squared feet after t seconds. Now here is a picture of what's happening. So this blast launches the rocket up really high, I don't know, and then comes back down. So we are going to graph its position in y1 to answer part A. How high does the rock go? So what is its highest position? So I'm going to put the position curve into y1. So that's 160t minus 16t squared. And I did second calc max, and how high does it go? That would be 400 feet. Now that happened at 5 seconds, but it was 400 feet. Now part B asks, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Well, first of all, velocity is a change in position. How fast is its position changing? So that is the derivative of position. So velocity is s prime. All right, well, let's find s prime first. So s prime, I'm going to see the derivative of 160t is just 160, the constant. Now I'll drop the 2 down as a coefficient, so negative 32t to the first. So there's s prime. But I need to know what number to plug into s prime. It says, what is the velocity and speed of the rock when it is 256 feet above the ground? So that is talking about a position. We're asking, when does its position equal 256 feet? So back to my position graph, that happens at 2 places. On the way up at 2 seconds and on the way down at 8 seconds. So now I'm actually being asked, what's s prime of 2 and what is s prime of 8? And it should make sense, since this graph is symmetrical, that 256 feet, the velocity on the way up would be positive 96, and then the velocity on the way down would be negative 96. But it's asking for what the velocity and speed of the rock are. So the velocity would be 96 feet per second, and negative 96 feet per second. And then we can make the conclusion that the absolute value of s prime of 2 would still be 96 feet per second, and the absolute value of s prime of 8 would also be 96 feet per second. So there we gave both the velocity and speed of the rock on its way up at 256 feet above the ground and on its way down at 256 feet above the ground. Whew, I'm exhausted. What is the acceleration of the rock at any time t during its flight after the blast? So acceleration is the derivative of velocity. It's the change in velocity. How fast is a velocity changing? Well, s prime, which we probably should have said also equals v of t, was 160 minus 32t. Now, v prime of t is going to be the acceleration of t. So the derivative of the velocity here, let's see, derivative of 160 is 0. So now the derivative of negative 32t is just negative 32. So it actually doesn't matter how many seconds have passed, what second we're at. The acceleration will always be negative 32. And then what unit will that be? Well, that's going to be feet per second, the velocity, per second. So the change in velocity. Negative 32 feet per second per second. So we're starting out very fast. Our initial blast was 160 feet per second. And then we slowed down, which you see here, because after 2 seconds we're only at 96 feet per second. And then we keep slowing down. Well, actually, we keep slowing down until we hit the top, but then our velocity is still decreasing, so our acceleration is still negative 32 feet per second. At this top here, our velocity is 0. a horizontal tangent. Then as we fall down, now we're in negative 96 feet per second. So we still are losing 32 feet per second every second that goes by. Part D asks, when does the rock hit the ground? Well, that would be a second calc 0 thing, or I could just set the position equal to 0. When does the rock hit the ground is talking about when is its height or position 0. And we knew that the rock started from the ground, so t equals 0 seconds doesn't tell us when it hits the ground. It hits the ground at t equals 10 seconds. Number 13, lunar projectile motion. A rock thrown vertically upward from the surface of the moon this time at a velocity of 24 meters per second or 86 kilometers per hour reaches a height of s, so again its position is a measure of height, fine, 24t minus 0.8 t squared meters in t seconds. Find the rock's velocity and acceleration as functions of time. So if there is a function of time, we're not looking for an exact number, we're just looking for an algebraic expression. And it makes a note that the acceleration in this case is the acceleration of the gravity on the moon. So this won't look as familiar to you because it's the moon's acceleration of gravity, not Earth's. So here we go. S of t, the initial, the position equation is 24t minus 0.8 t squared. So that means that s prime of t is going to equal our velocity graph, which is, let's see, 24t. The derivative of that is just going to be 24 because t is now going to be the 0 power. 2 becomes a coefficient, so I get 1.6 t now to the first. So velocity is 24 minus 1.6 t, and that's going to be measured in meters per second. This guy up here was meters, just our position. And then now if I take the derivative of velocity, so s double prime of t, which is v prime of t, or acceleration, so acceleration is the second derivative of position. Derivative of 24 is 0, derivative of negative 1.6 t is just negative 1.6, and that's going to be meters per second per second. So the acceleration, again, doesn't depend on what time it is. It's just going to be a constant acceleration of always losing 1.6 meter per second every second. Part B, how long did it take the rock to reach its highest point? Well, that's talking about the rock's position. So I put the position graph, found a good window, and found its maximum. How long did it take to reach the highest point? 15 seconds. And then question C asks, how high did the rock go? That's going to be 180 meters. D asks, when did the rock reach half its maximum height? Well, its maximum height was 180, so I need to know when it's going to reach 90. So I put in Y2, 90, and there are two places where the rock hits 90 feet, once on the way up and once on the way down. So that's going to be at 4.39 and 25.61 seconds on the way up and on the way down, respectively. And part E, how long was the rock aloft? Let's see. I found the 0, and the rock hit the ground at 30 seconds. So for 30 seconds, it was in the air. Not too much calculus involved in that problem, but part of the calculus challenge is that they're going to make you switch back and forth. Do you need to use in-depth calculus here, or can you use something else? Now, usually you have to use calculus in every problem, but as we are starting our learning phases here, they want you to switch back and forth, basically just to test you on whether you know if you have to use the position graph to find your answer, the velocity graph to find your answer, or the acceleration function or graph to find your answer.